Hello, everyone. Hope you're doing well. We're at our very last video lecture of content here, talking about this last concept, which will be the concept of category. Now, this is one of the big C's that we didn't get a chance to talk about until now. The big C's that we've discussed so far are compactness, continuity, convergence. We've talked a little bit about completeness as well as connectedness of a space. But another big C is that of category. And the reason that we haven't talked about it until now is that we haven't found much use for it. I've been dragging you along a little bit with some of these objects here to say a lot of the ways that we design this class is around this notion of a Fourier series. Of course, Fourier series themselves are a very optional topic for this class and aren't really required of knowledge for what we're kind of doing here. But I do think it is a great motivator for why we go through the material at the rate at which we do it. So talking about the Baire category theorem and what categories are, I want to give a little bit of motivation before we move into what this theorem is. This is something completely new to us, but it is involved with the notion of density from before. So let's recall real quick what that definition of density is. We would say a set S is dense in T if for all open subsets, and I should add in here non-empty, for all non-empty open subsets U of the set T, U intersect with S, it's non-empty. What that means is that every open subset of the space T intersects non-trivially with the set S. The great canonical example of this is that the rational numbers are dense in the real numbers, because any open subset you have in the real numbers is going to contain an open interval, and any open interval contains, in fact, infinitely many rational numbers. So to say something is dense is to say that whenever you take an open set inside of your space T, then its intersection with the set S is non-trivial. We're going to talk about a kind of a polar opposite of that definition today, which is the definition of nowhere dense. And we're going to be defining a Meager set to be a countable union of nowhere dense sets. The opposite of that notion of Meager, kind of trying to come back a little bit to what density might look like, although it's not quite exactly the same, is the notion of Comeager. And that is a definition that ends up being very useful in the understanding of Fourier analysis. And the way it comes in is with this theorem that you see up here on the screen. This is not something from our reading. This is something from chapter 8 of this textbook that I went through and dug through to see what is it that we work through Baire category theorem for. And a big reason behind that is that a major theorem from Fourier series tells us that the amount of points from where a Fourier series diverges is quite large by an important measure. Just as a quick, brief kind of disclaimer here, many times when we look at a space of functions and we want to say, does the Fourier series converge or diverge? We've seen many examples where it does converge because our functions have been continuous. Continuous functions on a compact interval Fourier series are going to converge uniformly, in fact, to the function they converge to. However, if we define C sub p to simply be the set of periodic functions, no boundedness condition, no continuity condition, and ask for us to get a set of Fourier series for that function, which are still well defined. They are these inner products of the function with the standard basis elements of sine of nx and cosine of nx together with 1 over square root of 2, just like we talked about last week. Well, if you go through and define these things, you get an infinite sum still of functions. And the question is, do these Fourier series converge to the function f that I started with? In fact, the Fourier series typically don't converge to anything at all. The set of all of those functions, again, with no continuity or boundedness restrictions on those functions, the set of all of those functions f, where the Fourier series of f actually diverges at a given point inside of a closed interval from negative pi to pi, for example, is Comeager inside of the set C sub p. Comeager for us is going to mean the opposite of a Meager set, which is, again, a countable union of nowhere dense sets, which we will be discussing as a notion of like a very large. Comeager is going to be a very large collection of points inside of our set. So that's what a big reason behind motivating this sort of discussion is here. And what we'll see in today's video lecture is that not only is this useful in the context of Fourier analysis, it's also useful to be able to determine many things about norms on specific spaces, or things about functions that maybe seem obviously true to us, but we actually don't have any other way to prove except through the Baire category theorem. So that's going to be our thrust forward for this particular video lecture. So let's get started here with some of this notion. Something I want to mention here about this, which I think is a good thing to be discussing, is this notion of nowhere dense, and get a definition here of this for us. When I go through this, I'll also be keeping tabs of some of the cardinality conversations that we've been having. For example, when we say Q is dense in R, we know Q is countable and R is uncountable, and yet Q is still said to be dense in R just because of how R is defined in the first place. Remember that we said that the real numbers are a completion of the rational numbers. The complement of the rational numbers is the set of irrational numbers, which, by the way, is also dense in the real numbers. Every open interval inside of the real numbers contains both infinitely many rational points as well as infinitely many irrational points. What is an appropriate opposite to density is, I think, a very good question. Remember that the notion of density is to say if you're looking at the real line and you're looking at any kind of open set inside of there, then there is some way for you to still be able to find points of the set that you're looking at. If this is like Q, for example, all of these little points all the way through here, then this is an example of a dense set because any open interval is going to be containing some of these points. Appropriate opposite of this would be something that basically you don't have this open set property. You're basically saying, okay, it's not true that for every open set you have a point inside of there. Now, maybe the exact opposite that you think of is that for every open set, the open set U intersect S is actually empty. But that actually just tells us that the set S that we're working with has no points in it at all, that S is equal to the empty set. So that doesn't seem like it captures enough of an opposite to that. The empty set and the entire set seem to be opposites, rather than a dense set and a nowhere dense set, if we're going to give nowhere dense that sort of definition. So maybe we want to add a little bit more to that definition. Let's say that we take some sort of open set inside of the space T. So here we're getting a notion of why we're giving the definition that we do for S being nowhere dense inside of T. Let's say we take an open interval, and we'll just use the real numbers as a context, and let it be a subset of T, our major set T here. Now, again, if we say that for all open sets U intersect S is equal to the empty set, then in fact, S is the empty set. There's no other way because we could just say at that point, well, we could just substitute the entire set T to be equal to the space U because the entire space is open inside of that space. So then at that point, we then get to claim that S is empty itself. So we don't want to just write that as our condition of nowhere dense. We want to try and change this a little bit. So what we'll say is whenever you have an open interval U instead of T, there exists a further non-empty open set V, which is inside of U, such that V intersect S is equal to the empty set. So if you have some sort of open interval here, sure, maybe you have some points of your nowhere dense set in here, but you could still go a little bit farther to find another open interval inside of the bigger open interval that has no points from the set inside of it. And that's actually our definition here of nowhere dense. I'll use a couple of different letters, kind of going in line with what the textbook reads. We will say that a subset S of a metric space X is nowhere dense if it isn't dense in any open subset of G inside of this space X. That is, if you have an open subset G, there exists a further non-empty open subset H, subset of G, such that its intersection with S is empty. Of course, we need to be asking as well that these are non-empty open sets G as well. Otherwise, we cannot get a non-empty open subset of G to make that happen. So we're always working with open sets that are not the empty sets in these definitions. So a quick example of something that is nowhere dense is going to be the natural numbers. Kind of going back to our example here with the reals, we just write the natural numbers here like we would on a typical number line. Then any open set that I might give, and I'll just write an open interval down, of the real numbers can intersect non-trivially with the natural numbers. However, if I am allowed to find a further non-empty open subset that has that I want to have no intersection with the natural numbers, then I absolutely can do that. I can take a smaller open interval inside of the bigger open interval that I'm given that gives me a trivial intersection now with the natural numbers. So this is showing us that the natural numbers n is nowhere dense in the real numbers. So this gives me this example. Let's play around with this definition a little bit. Let's start here. Let's prove, oops, I'm going to have to pause out and come back here. And let's negate this statement that the set S is nowhere dense in X. First thing I'm going to do is write out this definition of nowhere dense that we have up here, utilizing our logical notation. So negating the statement S is nowhere dense in X, we'll start with the actual definition. S is nowhere dense in X is going to mean what? Let's check this out. That if you have, so first, if we write it in the way that we see in this second sentence here, and then we're going to have, whenever you have an open subset G inside of X that is itself non-empty, so here you can see I've written that G is not equal to the empty set, and G is a subset of X, so just writing those two things together, then there exists an non-empty open, so this is, once again, an H, a subset of G. So there exists an open, non-empty subset H, subset of G, such that H intersect with S is the empty set. So this gives us this example for how to show S is nowhere dense in X. This is the logical notation for how that works. This little compound notation is telling us that G is not equal to the empty set while also being a subset of X. This one is telling us that H is not equal to the empty set as well as being a subset of G. So now let's go through and negate this definition. So to say S is not nowhere dense in X is what we're going to be working through now. This is important because when we do a lot of these definitions of what is to come, we're going to be seeing a lot of this sort of way of writing it. How do we want to understand if something is not nowhere dense, giving a not example of things like this. So what we'll be saying is if something is not nowhere dense, we're going to be basically saying it's dense somewhere. That should be the way that we understand this. That is, it should be dense in some sort of non-empty open subset of X. To say that something is dense inside of there is to say that there exists an open subset G inside of X such that for all open non-empty subsets of H inside of G, that H intersected with S is not equal to the empty set. So this is saying that the set S is dense somewhere. To kind of clarify what we mean, we could be looking at something that maybe when we start building it looks a lot like the natural numbers. But maybe there is a particular open set, which we might call G, where the set that we're looking at actually looks a lot more dense than it does elsewhere inside of the graph. And inside of that open subset, it has the density property. Whenever you take an open subset of that set G, then its intersection with the set S that you're working with is non-trivial. It is a non-trivial intersection between the two sets. So an example of something that maybe is not dense, but not nowhere dense, is that you could take the natural numbers, something like this as a place to start out with, but maybe you union it with the rational numbers intersected with the interval from 0 to 1. This is an example of a set that would be not dense, because if you try and graph some of the open intervals that you have over here, you can definitely get open intervals with trivial intersection with the natural numbers. But over in this point, you could say, okay, well, let G, the open set, be the open interval from, like, say, going from 0 to 1. And then any open interval that you include that is a further subset of 0, 1, itself intersects with the rational numbers. So this is an example of something that kind of lies in the in-between. It's not quite dense. It's not quite nowhere dense. It's somewhere in the middle. So this is what it means for something to be not nowhere dense, that for some open set inside of X, the set S is dense. And that's another way that I could write this. For some non-empty open set, G, S intersect G, I should say, is dense in the set G. So the part of S that is inside of the set G, in this case, looking like right over here, then that is going to be dense inside of the set G. So that's another way to write that something is not nowhere dense. Notice that this is going to change a good bit if we know some things about the set S. We'll actually go through and say that if the set S is closed, then we actually get a lot of information from this. Because to say that something is dense is to say that its closure is equal to a particular space. And if we know S is already closed, we actually know an equality between sets this way. A little bit kind of similar to how we might in using Stone-Weierstrass or something like this. We can oftentimes get density in a space of continuous functions on a compact set by utilizing that theorem. But if we happen to know that the set itself is also closed, we actually know that the two sets are equal to each other. And we've used that a little bit last week as well as in some of the weeks prior. So we're going to be doing the same sort of thing. Here, if we have a space that is dense inside of another one, if we happen to know that we're looking actually at a set that is already closed, then it's actually going to be equal to the set G. Whenever I consider, say, for example, S intersect G is going to be equal to the set G. We'll see an example of that come up, but just kind of giving a heads up that that is a typical way that this is implemented. Let's see another way of formulating a set being nowhere dense inside of X. This one also was not given in the textbook, but I sometimes find this useful whenever I'm trying to prove things with the Baire category theorem, so I thought I would offer it as well. Because we just were talking about how you can look at the closure of something and start determining things about whether or not you have this sort of notion of density. In fact, if you have something that is not nowhere dense, then what's happening? S bar is equal to the open set that you have. Well, if S bar intersected with the open set that you're looking at is equal to some open set, that means something about the interior of the closure. Recall that the interior is all of the interior points of a set. So for example, if I'm looking at the interior of 0, 1 as a closed interval, then that is equal to the open interval from 0 to 1, because this includes all of the interior points of the closed interval from 0 to 1. A set S is nowhere dense in X if and only if, meaning that this is another good definition. Whenever you take the closure of S and then consider its interior, you're looking at something empty. So let's go back to the natural numbers example. The natural numbers we know is nowhere dense inside of the real numbers. So to try and understand how this theorem might work, we could start by trying to take the natural numbers and look at its closure. Recall that the closure of the natural numbers includes all of the boundary points, accumulation points, however you like to call it, all of the points that are limits of sequences inside of the natural numbers. Well, if I have a sequence of natural numbers, no matter what they are, and I know that this sequence converges, well, then I know something about that sequence. It has to be eventually constant. The natural numbers is a discrete space, and it operates very much like the discrete metric in that sense. If you try and take a sequence of natural numbers and get them to converge, they have to be eventually constant. So the closure of this space, the natural numbers, ends up just being the natural numbers. If you're going to get the natural numbers to converge at all, then you're going to have to make sure that they're eventually a natural number themselves. Hence, they would have to converge to a natural number. I don't grow the space of natural numbers by taking its closure. This is another way of saying that the natural numbers is itself closed. No need to do anything extra on top of that. However, the interior of the natural numbers, that is, what points of the natural numbers would be an open set of an interior point in the real numbers? Well, if we're looking at the natural numbers, we don't have any open interval that includes only natural numbers inside of that open interval. So that tells us that the interior of the natural numbers is the empty set. No point inside of the natural numbers is an interior point. So that's an example of how this theorem works. The natural numbers was nowhere dense in R, so the closure of the interior is the empty set. Let's walk through this proof very quickly. All we're doing is we're utilizing our previous example of how we showed that something is nowhere dense, and then utilizing that definition to work in either direction. So if you start with a set S, that is, so proving this one by contrapositive, this one actually says that this is S being not nowhere dense, is what I should have said here. S being not nowhere dense, that always feels like a contradiction. It feels like you should be saying dense. It just means somewhere dense, which means that S is going to be dense in some open set G, which by definition means that the closure of S is going to contain G. That's that notion of when you say you take a look at the closure of something, like say, for example, you know, S intersect G is dense in G, then that's going to imply that S intersect G closure is equal to G by our definition of what it means to be dense inside of a set, that the closure of that set is equal to the entire thing. Since G consists of interior points, the interior of closure of S is non-empty as desired. To say we have a G inside of S bar means that we have tons of interior points. We have all of the interior points that are inside of the open set G. Now to go in the opposite direction, we're going to prove by contradiction. Let's say that you have a set that is nowhere dense, and let's the closure of the interior of the closure of the set S be a non-empty set. And let's see if we can derive a contradiction from this statement. Well, the interior of a set is going to be an open set itself. So in order for S to be nowhere dense in X, we have to utilize this definition. So first, the interior of a set is open, and we know that the interior is non-empty as a part of our contradiction. So we're trying to derive a contradiction in this, starting with, S is nowhere dense in X, and the interior of the closure of S is non-empty. So we have a non-empty open set to be working with, namely the interior of the closure of S. So let's use this in the definition of nowhere dense. If we use that, then we're going to get another open subset H, which is a subset of the interior of the closure, such that H intersect S is actually going to be equal to the empty set. By this statement, no point in H can be a point in S because their intersection is trivial using that definition of nowhere dense. Also, no point in H can be a boundary point of S. If you take a point inside of H, and then since H is open, there exists a real number that could be a radius for this, such that the ball centered at that point H of that radius is completely contained in H, but we still know that H intersect S is non-empty. So in fact, the open ball intersected with S is still empty. What we've just shown is a contradiction. The contradiction is, what we've seen is that H is intersect S is non-empty, and that in fact, no point in H can either be a point in S or can be a boundary point in S. So that means there's a contradiction since no point in H can be in S bar. Because no point in H can be in S, and no point in H can be a boundary point. Recall that we define the closure of the set to be the union of the points inside of that set with the boundary points of that set. So there can be no point in H inside of any of these, but we just said that H was a subset of G, or rather was that H itself was a subset of the interior of the closure of the set, which is itself a subset of S bar. And this gives us a contradiction. Where is it coming from? H is a subset of S bar, and yet somehow no point in H can be inside of S bar. So that is a contradiction. We assumed H to be some sort of non-empty open set inside of S bar, and yet no point in H can even be inside of S bar. There's our contradiction. This gives us two things that cannot exist inside of the same space. The only thing that we assumed in this was that S bar interior was non-empty, and hence S bar interior has to be empty as a result. So there is our contradiction here for this proof. You can kind of see now how these examples play out. The natural numbers being nowhere dense in the real numbers, we can start playing around with some of these pictures using either one of these two definitions. It's whichever one that you would like to work with in a given context, whatever feels like it is the best to work with. I like using both of them. Both of them kind of work very neatly for me, depending on what kind of situation I find myself in, whether I want to be using the open set definition or the closure interior definition for nowhere dense. I'm typically playing between both of those definitions to make this work. So that gets us through nowhere dense. And these are meant to signify very small sets. Notice that the natural numbers, as an example, is a countable set that lives inside of the world of uncountable real numbers. There is a whole cardinality difference between the two sets that we're working with in this notion of nowhere dense. Now, that doesn't mean that every countable set inside of the real numbers is nowhere dense, because we have the rational numbers as well. The rational numbers is not nowhere dense in R. In fact, the rational numbers is dense inside of the real numbers. Looking at the closure and interior of this space, if we take the closure of the rational numbers, we get the real numbers. We take the interior of the real numbers, we get the entire real numbers. So this is showing us kind of a polar opposite of what nowhere dense is supposed to look like. If you take the closure interior of this set, then you get the entire space. That shows us a very contrasting difference between how the natural numbers and the rational numbers work in terms of density with the real numbers. So not every countable set is going to be nowhere dense, but typically examples of nowhere dense sets are on a level of cardinality beneath the space in which they live. Typically, like what we see in nowhere dense set inside of something like the real numbers, the natural numbers are going to be a whole level of cardinality beneath that of the real numbers. So taking a countable union of countable sets, remember, is itself countable. So if we are taking a countable union of these nowhere dense sets, it should not do much to their relative cardinality or size, as long as our space is suitably large. So for example, if I took the natural numbers and I continued unioning the natural numbers together to make, say, like maybe we took the natural numbers plus any rational number. So like looking at all of the 1/2, 3/2, 5/2, 7/2, and then continue to union parts of the natural numbers together in picture form. Maybe you're looking at this. Here's the natural numbers, -2, -1, 0, 1, and 2 that I might use as a set 1. Then if I union those with another set, that is maybe -3/2, -1/2, 1/2, 3/2, so on and so forth, as a second set here. And if I continue to do a similar unioning of nowhere dense sets for, say, even up to countably many of these nowhere dense sets and continue to build sets in this way, then I would get what is called a Meager set, which is a countable union of nowhere dense sets. A set is called Meager if it is a countable union of nowhere dense sets. So imagining here, for example, the natural numbers and continuing to shift them by a rational number, the way that we've been defining that so far in our homework has been like this. You could take the union of the natural numbers plus q. The natural numbers plus q, recall, is taking all of the natural numbers and just adding the value of the rational number to them. This is a countable union of just translates of the natural numbers. Each of these is a nowhere dense set. And the countable union of a nowhere dense set is Meager. So we have to have first two things. Every set that we are unioning together is nowhere dense. And the second thing is that the index by which we are unioning together these nowhere dense sets needs to be countable. I'll show you a reason why we actually ask for that to be countable here in just a little bit. But let's start with the framework here with this example with the rational numbers. The rational numbers itself is a Meager set. We'll start by helping to understand what that means. Recall that in order to show that the rational number is a Meager set, we're going to need to show that it is a countable union of nowhere dense sets. Here is that countable union. We're going to union together using the indices of just all of the rational numbers, just like we did in the example to the right of this slide. And the sets that we're going to be unioning together are going to be these sets. for every rational number that I might union over, I'm going to consider the set containing just that rational number. So for example, I might be just writing 1, -1, 2, our union with 1/2, and then -1/2. And then maybe I'll have 2, and then -2, so on and so forth, all the way through to get to all of these rational numbers. So I definitely will have a countable union here. The indices that I'm working with are the rational numbers, and we've shown the rational numbers are countable. But are the sets that we are looking at, like the set of 1 or the set of -1, are these all nowhere dense? Let's take a look. If we have a singleton set, we need to ask a few things. Either for any open set, there exists a subset of that that has a non-trivial or trivial intersection with the set, or we need to be taking a look at the interior of the closures of each of these sets. Let's just start with the set 1 and note and understand that the way that we work with the set containing 1 is the same way that we would work with any of these other sets. That is, if we show that this is a nowhere dense set, all of these should be nowhere dense sets because they're just translates of the same set. Well, the closure of a point like the set here is just going to be looking at all of the limit points of sequences that exist inside of this set. There's only one sequence that you can make out of elements inside of this set, and that's the set sequence of all ones. The closure of this set is just going to be itself because the only sequence that you can make out of elements inside of this set is the sequence of all ones. So the only limit point is 1. So it contains all its limit points. It is closed. What is the interior of this set? What is the interior of the set containing 1? Well, the only point that we need to check to see if it's an interior point or not is the point 1. And 1 is not an interior point inside of the set containing 1. Any interior point would have to be inside of an open interval at some point, and there's just no open interval that could fit inside of this set. This is the empty set. So in fact, that shows us by definition that this is a nowhere dense set. And the same thing is true for each of these other singleton sets. This is one of the most common examples of a nowhere dense set. Singleton sets are typically nowhere dense. We'll see an example in our homework where sometimes that is not the case. It depends very much on the metric that we are using for our space, whether or not that is true. The same argument, by the way, says that the rational numbers is meager in itself, because you can now take a look at all of these singleton sets and can still do the same thing. Taking a look at our notion here, the closure of a singleton set inside of the rational numbers is still that singleton set. And taking a look at the interior points, well, any open interval inside of the rational numbers, even if you take a look at the rational numbers, just all of the points in the rational numbers here, then any open interval is still going to contain infinitely many rational numbers. And we don't have infinitely many rational numbers here. We just have the 1. So this is still going to be equal to the empty set. The rational numbers themselves are a countable union of nowhere dense sets, which says that the rational numbers is meager in itself. Not just a meager set inside of the real numbers, but actually meager in itself. And that last sentence is going to be very important to us in light of the Baire category theorem. So that's getting us kind of to where we would like to go. So meager as a definition says that a set is the countable union of nowhere dense sets. The complement of a meager set is going to be called Comeager. And that tells us a little bit about what we were doing back on the first slide. We had a Comeager set of functions for which the Fourier series for that function diverged at any given point. Now that's pretty wild. That's a lot to take in. The fact that when you're looking at the functions for which Fourier series work, you're looking at a very small set. You're looking at a countable union of nowhere dense sets, something at the level of a whole cardinality lower than typically than the set that you're working on. So this same argument says that the rational numbers is meager in itself. That last sentence is what I want to be carrying over into this next slide. Because the following theorem says that if you add one thing to the metric spaces that we're working with, if you add a notion of completeness, then complete metric spaces are suitably large enough that they cannot be meager in themselves. This corollary ends up being one of the most useful utilities that comes from the Baire category theorem. It says that whenever you have a complete metric space, X, then X cannot be a countable union of nowhere dense sets. That is, X is not a meager set. So let's think about maybe intuitively why completeness might make a big difference here. Remember back in week 5 when we talked about how the completion of Q was R. And we talked about how we form the completion. You're not only taking a look at the values of the rational numbers, you're looking at all possible Cauchy sequences of the rational numbers. You quotient them out by some sort of equivalence relation that says if two Cauchy sequences seem like they're getting closer to each other, then we're going to define them to be the exact same point. That is the completion of the set. Well, so the completion of the rational numbers giving us the reals gave us a whole level of cardinality difference between one space. So this is the space of uncountable, and this is an uncountable set. So this, adding just the completing values of this, vastly, and typically does, vastly increases the number of elements that we are looking at inside of the set. The completion of any space that we might look at is going to up our level of cardinality. So if we are looking at a set that could be meager in itself, a countable union of nowhere dense sets, then maybe we're looking at something that is already pretty small to begin with. Maybe we're looking at, say, for example, a countable union of countable sets, which is itself countable. But that makes sense now that the reals cannot be a countable union of nowhere dense sets. If we're looking at something like the natural numbers here, for example, then we're trying to do a countable union over that in a similar way to how we worked on it before. Well, these two things cannot be equal. These are all countable sets as they are translates of the natural numbers, which is countable, and it's a countable union of countable sets. So this itself is a countable set, whereas the real numbers themselves are uncountable. So there's almost like a cardinality argument that you want to make. Our proof is not going to involve cardinality, but it does give us a good picture as to where this sort of stuff is coming from. It's saying that if you take all of these nowhere dense sets and take a countable union, they're not changing that much in like the size of where you could be going. You're still going to be looking at a very limited set of your set X. And if you're looking at a complete metric space, well, that complete metric space is going to typically be a lot bigger than you could get to from looking at a countable union of nowhere dense sets. Now, I've been utilizing cardinality as a way to evoke an image here for what category means, but category itself is still a very different notion than cardinality. Nowhere dense sets can very much be uncountable. They absolutely can be. In fact, taking a look at the space of functions and looking at nowhere dense sets inside of there, you absolutely could be looking at uncountable sets inside of the space of functions. And that's because the space of functions is so much bigger than the real numbers. You can imagine putting a real number at every single point on the real numbers. That's exactly what it is when you define a function. So nowhere dense sets don't necessarily have to be countable. They could be uncountable sets. So there's no direct correlation between the two things. I'm just using these as examples to help us understand where the notion of category comes from, connecting it to this notion of size. Now here I do a quick proof of the corollary given Baire category theorem, but first, let me actually go through and talk about the Baire category theorem. This is the thing that we typically use to prove this corollary, which ends up being very useful to us, which says that if you have a sequence of open and dense sets inside of a, note, complete metric space, we're going to need completeness here. Whenever you see complete, you automatically think we're probably going to be using Cauchy sequences and saying that they converge somehow. We're not going to be able to get an exact limit, but that's okay for a complete metric space. If you take a sequence of sets that are open and dense, then the countable intersection of those open and dense sets is also dense inside of the set X. So basically, think of this theorem, what it's saying. All of the sets that you're looking at themselves are open and dense, but you could be moving them around however you would like for each use of n. And you have countably many of them, so you have a lot of things to be moving around with. Then when the intersection, you are taking all of the points, only those that are inside every single use of n that you might find, and putting those all together into one set. It is saying that the intersection of those points, that even if you try to move around each of the sets use of n, you did not actually remove that many points from the intersection at all, no matter how you wanted to move things around. The intersection of the use of n is also going to be dense inside of the set X. Let's talk a little bit about how that theorem is proven. In order to show this, we need to show that if you have a non-empty open set inside of X, then W intersects this intersection as n goes from 1 to infinity of U sub n. Here, again, the U sub n are these open and dense sets. So what we're going to do, and our goal for this, is going to be to try and break apart this intersection of sets. This n goes from 1 to infinity of U sub n. We want to show that this open set intersects non-trivially with this intersection, and we already have some non-trivial intersections to work with. Because U sub 1 is already an open and dense set, we know that its intersection with another open set is going to be open, because it's an intersection of open sets, finite intersection that is, and non-empty. So because it's non-empty, there's a point inside of it that is an interior point, and we can call that point x naught. And because it is an interior point, there is an open ball that surrounds that point, and that is in fact completely contained within this intersection of U1 intersect with W. Now, we're going to make a quick condition on this ball before we move on, and this is really just for the sake of posterity. You can imagine these balls doing this as we move along. We're going to assume that the radii on this ball are continuing to get smaller. So we'll go ahead and shrink this radius to be less than 1, just in case that's necessary. Now we'll choose x sub n and r sub n inductively. Remember that an inductive process means once we've chosen this on the 0th step, this is how we will choose it on the first step. And then on the first step, this is how we'll choose it on the second. We'll basically choose something on the nth step based on the step that came directly before it. Having chosen some x sub k and r sub k so that there's an open ball that is completely contained within u sub k minus 1, and this open ball, we're now using this as our way of talking about this set W. We are making a replacement of the open ball that we got from the previous set, because now if we take this open ball and intersect it with another open and dense set, like U2, then that's going to be open and non-empty. And what we're going to be able to do is inside of that intersection, we can find another X1 and R1 to be working with. Now, the intersection of that set with U3 is also going to be contained within it's also going to be open and non-empty. And so we're going to be able to find another open ball that's contained within it. You may be able to see what this process is doing. Because each of these are open and non-empty, due to the fact that we're here using that U2 is open and dense. Here we're using that U3 is open and dense. Here we're using that U4 is open and dense. To say that each of these is open and non-empty, we can now find an interior point in each of those, which means that we can find another open ball. And that's exactly the whole process that we're using. We can observe that once again, that this intersection, this should actually be U sub k, intersected with B sub k, X sub k, R sub k, that going through this process is once again open and not empty. So we can choose a further collection, another point inside of, this is a point inside of X, and R sub k, some radius that's greater than 0, such that this ball is completely contained within this intersection. In fact, we can choose it if we want to choose, and we can shrink our radii a little bit further. We can actually make it so that the closure of these sets is in there. So say, for example, you have a ball X sub 1, R sub 1 that exists inside of this open interval. You could actually go a little bit smaller if you wanted to, R sub 1 over 2, and say something about the closure of that set, if you would like. That the closure of this open interval is going to be inside of this larger space. So we'll use that and replace R sub 1 with that smaller radius so that the closure of each of these can fit within there. We still want the open balls themselves because we want our intersections to still be open. U3 being open and this open ball being open allows us to have an open and non-empty set to be able to get another interior point in the set that's contained within. However, we should note that there is definitely a process that we are caring about here, which is that the closure inside of each of these is inside of these open balls. And that process continues to go all the way down. What is ending up happening is we're getting closer to a problem that we talked about in one of our homeworks. I believe this would have been homework 4 or 5. Let me take a look at that real quick. Here is the question I'm talking about, which was on homework 4 for us, which is to let you take a collection of subsets inside of a complete metric space so that the sets continue to grow smaller and that the diameters converge to 0. Well, we've been fixing our radii to continue to get smaller and smaller each time. You remember in our first step, we made the radius less than 1. And if you keep reading through that proof, we want our radii to eventually be less than 1 over k. So we get this whole sentence here. Then if you take a sequence such that a sub n and a sub n for each n and n is inside of these sets that are continuing to grow smaller, then if x is complete, this sequence of a sub n actually converges. What that means is that you get a sequence that converges, and the converging elements, the points at which you're converging to, is inside of the intersection of all of these sets a sub n. It's inside of all of them. What you've done is you have found an element inside of this intersection of all of these a sub n. That's actually kind of an unintended side consequence of this theorem, is that you've shown that the intersection of these a sub n is non-empty. That's actually a big deal here. And in fact, exactly that idea is what we use inside of this proof. Namely, the intersection of these a sub n is non-empty because it has to contain the limit of this sequence. This sequence is eventually within a sub n for all n, in which case you are going to be looking at a sequence whose limit is also inside of a sub n for all n. That's the definition of being inside of the intersection. So coming back to our proof then, so far what we've gotten is, and just to show you what I mean, here is where we're saying that our radii, our r sub k, have to continue to grow smaller and smaller to make this sort of theorem work. Then the radii is going towards 0. You have x sub n inside of these balls. This sequence x sub n then has to be Cauchy. This is what we did in our proof. X is complete, so this limit exists, and it's inside of these balls for each and every one of the balls that you might choose. Well, the balls are constructed so that they're nested within each other. That's exactly what we were doing over here in this part of our process. That anytime that you construct a ball, it is completely within of a particular intersection. That this x is inside of an open ball, which is inside of this u sub n, which is inside of u sub n intersect with w. In particular, this x is inside of w. We started this whole process by saying that in order to start this process, we need to look at it saying any open set W intersects non-trivially with the intersection of u sub n. But x is something that is inside of that intersection of these u sub n. It's inside of each of these balls, so it's inside of each of the u sub n by our definition. So x is inside of here, and what we also have figured out is that x is also inside of w by looking at the other side of these inequalities and how we constructed it. We were always constructing these x so that they were inside of these u sub n, and we were constructing these balls so that they were contained entirely within the set W. And because of this, x is in W, x is in here, so x is in an element inside of the intersection of u sub n intersected with W, which means that W intersected with n equals 1 to u sub n is non-empty, this is true for all open sets W. And this is exactly the definition of the intersection of these u sub n being dense, is that W is a generic open set whose intersection with this set, and it goes from 1 to infinity of u sub n, is non-empty. And that's the idea behind this proof. It's really pretty clever. There's a lot going on and a few things to be kind of taken care of here, but it's neat that it kind of fits all on one slide. You are using this problem that we've been working on back in homework 4, together with continuing to make smaller and smaller open sets, having them all be contained within each other to make this work. Now that we've proven that part, we can briefly talk a bit about how we are getting this corollary that we use a good bit, which is, let's start with a sequence of nowhere dense sets inside of X. Well, every open set in X has a further open set contained in the complement of E sub n complement for each n. That means it has a non-trivial intersection inside of E sub n complement. Well, each of those points that you find inside of this further open set is going to be a set of interior points inside of E sub n complement. So the interior of that set is going to be open. Since this is true for every open set in X, that is another definition of density. That is that every open set in X has a non-trivial intersection with the complement of E sub n complement. So the closure, the interior of the E sub n complements is going to be an open and dense set inside of X. Well, the Baire category theorem just tells us that if you take these E sub n complements interiors and start looking at what each of these things is, you take their intersections, then goes from 1 to infinity. Each of these is open and dense, and hence so is their countable intersection. This is also open and dense. So their intersection is dense, or is not open. It could be, it's just dense. Their intersection is dense in X by the Baire category theorem, and hence it's non-empty. Since the union of E sub n, which is actually the complement of E sub n complement, since this is disjoint from this union of E sub n complement, we know that the union of these E sub n is not equal to X. So to explain that last sentence there, we've shown that this is non-empty, which means that if we go through and look at the complement of this set, so if we take a look at the complement of this intersection here, take a look at this complement, well, then this can't be the entire space. This can't be all of X. But recall that the complements, the way that you form a complement using our distributive laws and using properties of the intersection as well, that what we end up getting here is looking at this closure of the union of the closures of the set of the E sub n, not the E sub n complement, because the complement comes in inside of the bar as well. Remember also that to undo an interior, you're taking a closure for that complement. We talked about that a bit back in week 4 as well. So the union of these E sub n closures is not equal to X. In fact, that means that the countable union of the E sub n can't be equal to X either, as that's going to be contained within these closures. Another thing we proved back in week 4. So this union, as n goes from 1 to infinity, is a countable union of nowhere dense sets that we just started with and is not equal to X. And that's exactly the statement of the corollary, is that X cannot be equal to a countable union of nowhere dense sets. So the key behind this proof of the corollary is to say, look at the complements. The complements of E sub n, because the E sub n are nowhere dense, the complements of are open and dense. So we can now use the Baire category theorem on them. And then undoing what we've done, we get the corollary statement. Now, the statement itself and the proofs that lie within may not feel all that illuminating, but let me show you an example of what we can do now that we have Baire category theorem. This is a large way of how this theorem is typically utilized, is to start trying to make statements about what happens when you look at a sequence of functions on a given space, or something that is already known to be a complete metric space. You are writing it in a specific way to try and claim that if the problem statement that I'm working with is not true, then actually Baire category theorem is false, and kind of try and get a contradiction off of this. That's the way that we use Baire category theorem mostly, is that Baire category theorem is a contradiction machine. And here's how it's typically used. Goal. If we are given a problem to work with, we are going to attempt to write a complete metric space as a countable union of nowhere dense sets. If we do this, then we can derive a contradiction with the Baire category theorem. Now, it may seem weird kind of writing it in exactly this way, because I haven't told you basically how we start these sorts of proofs. Oops, gonna have to maybe rewrite this part real quick. Give me a second. Because how are you going to write a complete metric space as a countable union of nowhere dense sets if you're going to get started with something that is true anyway? And the typical thing that we do is we start with the problem statement by negating it. Negates the problem statement that you're attempting to show in an attempt to reach a contradiction. So you'll see how that works in this context. We're going to take this problem statement from this problem, negate it, and then use that to attempt to reach a contradiction. Our goal to get to that contradiction is to write a complete metric space as a countable union of nowhere dense sets. If this problem statement say the problem that we're given right here, is somehow false, then you can actually write a complete metric space as a countable union of nowhere dense sets. And by Baire category theorem, you have a contradiction. That is our goal with these problems. So let's see if we can start that with this problem. Let's start by negating the definition or what we're trying to show here with this problem. Recall that anything before that last sentence is just going to be context. This is the universe in which we live. Let the sequence of functions f sub n live inside of continuous functions from 0 to 1, such that you have this property. For each x inside of the closed interval from 0 to 1, there is some value of a natural number that relies on x. This x right here means that n relies on x. Think once I've specified what x is, I can specify what the natural number n is, so that f sub n of x is greater than or equal to 0 for any natural number that's greater than this point. To put that into a more clear way of writing it, anytime that you fix a point, there's going to be, for that point, a specific index of the sequence f sub n, so that past that index, the function's non-negative on that point. So on that point, at some point somewhere, the f sub n of x has to be greater than or equal to 0. Let's show that there is a natural number n and an open non-empty interval I, so that in fact, there is going to be a point at which you could say the same thing not only at a point, which is a very localized coordinate, but say it a little bit larger. On an interval, on an open non-empty interval, you can say that past a specific point, the function is going to be non-negative. So the picture that we have here is that you can imagine that for each time that you look at a sequence of functions, for any point that you might pick, there's going to be a point past which the function is going to be strictly greater than or equal to 0. Taking a look at our red lines that we have for here, then if we take a look at what this sequence of functions is, then eventually past some point, the red line is going to be strictly greater than or equal to 0. That y value is going to be strictly greater than or equal to, or not strictly, just greater than or equal to 0. It might be negative, like you see it being right down here. It might be 0 at some point. It might get to be positive. But past a certain point of our index, the index being the index for the functions that we're drawing, past a specific index, the function would need to be always greater than or equal to 0 at that given point. And our goal is to show that actually we could say the same thing about an interval, not just about a given point, that there exists a certain index past which all of the functions past a specific point are all greater than or equal to 0. Now, so this is something about a countable sequence that we want to show it has something that exists on an open, non-empty interval. Let's say that this open interval does not exist. So here's our proof. First, assume the opposite. So we are going to assume that the opposite in an attempt to reach a contradiction. So we're going to get to really practice our contradiction proofs in this section. In an attempt to reach a contradiction, let's assume the opposite. So we'll start by negating the statement. The statement will be that for all n in the natural numbers, and for all open, non-empty intervals inside of 0, 1, so this is for all open intervals, non-empty, there exists an n in the natural numbers that is greater than or equal to n, and then there's also an x inside of I, such that f sub n of x is actually less than 0. So if I go through and negate that statement, reading it from left to right, this is what I'm going to end up getting. For all, so this is, if we want to read it clearly, this is saying, whenever you pick a cutoff point, or whenever you pick an open interval, you can still find a point in that interval, whatever it is that you chose, and you can find a point past that cutoff point, whatever it is that that cutoff point is, so that the function is still going to be negative on that component. So this is the opposite of what we were trying to say before. Past a cutoff point, the function is always going to be non-negative on some interval. We are saying no matter the cutoff point, no matter the interval we choose, we can still find a point in a place past that cutoff point for which the function is going to be negative. Let's talk a little bit about what we're about to do. We want to write a metric space as a countable union of nowhere dense sets. So we've negated this proof here, and we're going to keep that just on this sentence here for a little bit. Let's now switch to the first sentence in this problem and start trying to use it to write a complete metric space as a union of sets. We're not going to say anything about nowhere dense yet, but let's see if we can write it as a countable union of sets using the information that we have right here. Again, we're focusing on the first sentence here. Let's take a sequence of functions f sub n, and then we have for each x inside of the set from 0 to 1, there is some n sub x, so that f sub n of x is greater than or equal to 0 for all n greater than n sub x. For this first one, I'm going to go ahead and write what this set is. Let's write s sub n, and let's define it to be the set of the following. We want this to be equal to, once we union all of these together, a complete metric space. And my goal for this one is to say that the union of these s sub n is going to be equal to a complete metric space that I see right in here. I have two complete metric spaces. I have 0, 1, and I have C0, 1. I'll go ahead and say that typically we're going to be using any subset of the real numbers as what we're trying to use as our complete metric space. So our goal here is to try and write the union of these s sub n as equal to the closed interval from 0 to 1, which is a closed subset of R, so it is a complete metric space. So let's take s sub n and see if we can write a form of s sub n that makes this work. Now, we know something about every single point x inside of 0, 1. Every single point inside of this closed interval from 0 to 1 gives us an n sub x, such that this f sub n of x is greater or equal to 0 past that point. Let's make that n. Let's make n equal to this value of n right here. So here's how I'm going to define it in a way that maybe will make sense as we read it through our proof. I'm going to write s sub n to be the set of all x inside of 0 to 1, such that we have x inside of 0, 1 as something to start out with. We're going to say that the set s sub n is going to be the set of all of the x that is inside of 0, 1, such that for all m greater than or equal to this being the index of the set s sub n, this is what we were talking about from before, that this index is going to be this cutoff point, this n sub x, and now we're writing this part of the proof for all m values greater than or equal to this n, f sub n of x is greater than or equal to 0. So first, let's make sense of the set that we have defined. This is saying that this is a subset of the closed interval from 0 to 1, and we're looking at the possibility that for all points past the cutoff point, where that cutoff point is the index of s sub n, that f sub n of x is greater than or equal to 0. So this is a subset of the closed interval from 0 to 1, and this is saying that past a certain cutoff point, we know the function is going to be greater or equal to 0. You might notice a few things about these sets. These sets are increasing. They're getting larger and larger as you keep upping the value of n. How do I know that? I'm making my cutoff point larger, past which the functions must all be greater than or equal to 0. And if I make that cutoff point larger, then I'm ignoring more and more functions as I continue to up my value of n. So because I'm just ignoring more functions as I continue to do this, that's going to continue growing the values of x, past which this value f sub n of x is greater than or equal to 0. In fact, they increase so much as to be the entire space, because for all x inside of 0, 1, there exists a value of n sub x in the natural numbers, such that whenever you look at n greater or equal to this nx, f sub n of x is greater than or equal to 0, you might notice that we're just writing this set again. Because this is true for all x inside of 0, 1, we actually have that the union of this unioning over all possible of these n sub x's, because for all x, one of these n values has to exist. This union of the s sub n is actually equal to the entire closed interval from 0 to 1. So let's take a look at what we've done so far. We've gotten to ourselves a notion that the Baire category theorem should work here. We've gotten a goal for in our minds to negate the problem statement to reach a contradiction. And the goal is going to be to write a complete metric space. So far, what we've gotten is just a countable union of sets. Write a complete metric space as a countable union of nowhere dense sets. So far, we've got countable union of sets. And then we're going to derive a contradiction to say that the problem statement is actually true. So right now we're about halfway done. Here's what we've done so far. We've assumed the opposite. We've just left the negation here that we're going to come back to in a second. And what we've done on top of that is we have written the sets S sub n, which we have shown is the union of which is equal to the closed interval from 0 to 1. The way that we wrote this set S sub n is we looked at the first sentence that we had and tried to write this in set notation form. That is, right now it's written in a very logical form, but how could we write this so that this works in terms of a set? And the way that we ended up working on it was that we said, if you take a look at these n sub x and the natural numbers, you could make that the index of a set S sub n. The n sub x that you're looking at could be the index of a set. So that's the connection of the logical statement that we're making together with the set notation that we're using this S sub n. And what we're going to define S sub n to be is going to be all of the points x, the things that we're trying to union to be equal to the entire set from 0 to 1, such that the rest of everything is true. The rest of everything here being for all m greater than or equal to this index that we've chosen from before, that f sub m of x is greater than or equal to 0. And that's exactly the set that we defined beneath. So far we've just written, after seeing that this works for each x inside of 0, 1, that the union of these S sub n, by definition of union, has to be all of 0, 1. We've now gotten to the point where we want to start showing that these sets are nowhere dense. And that's going to be our last part of this proof. Well, we have two ways to show something is nowhere dense. We can either show that for any open set, there's a further open set that does not converge with this, or we can show that the interior of the closure of the set is empty. Let's go back to the first part of our proof. And notice something interesting about it. Let's read it through one more time just to make sure that we're kind of all on the same page here. This is saying that regardless of the cutoff point n, and for all open intervals I, there exists a cutoff point in an x in that interval such that f sub n of x is actually less than 0. Let's see if we can utilize that to our advantage in using either one of these two definitions. So i.e., the interior of the closure of S sub n is empty. So let's see if that's something that we can do. First thing I'm going to claim, and this typically happens with these types of problems, first claim, is that I'm going to say that S sub n is closed. So S sub n is just S sub n bar. So these two things are equal. The reason that I'm going to say that is I'm looking here at this statement, and I'm looking at a space of continuous functions that are greater than or equal to 0. If I take x sub n inside, or I guess I should use a different index. I'll use x sub k inside of S sub n. So this is a sequence. So take a sequence, x sub k, that is subset of x sub n, and assume x sub k converges to a point x inside of 0, 1. We would want to show that x is inside of S sub n, in fact. But we do know that for all m greater than or equal to n, we have that f sub n of x, or f sub m of x, and x sub k, that is, f sub m of any element inside of the sequence x sub k is going to be greater than or equal to 0. And if we just fix this m, because that's not that big of a deal to us, just keeping the m there, and looking at the sequence of the x sub k, since we want to show that this set S sub n is closed, we know that because f sub m is continuous, so we're looking at a sequence of functions inside of C0, 1 here, then f sub m of x has to be greater than or equal to 0 by our comparison test. If you have a sequence of values that are greater than or equal to 0, then so is the limit. That also has to be greater than or equal to 0. By definition, then, x is going to be inside of S sub n, so S sub n is closed. All righty, good deal. So first thing we've done is shown that it is closed. Now let's take a look at the original statement that we came to begin with. You might look at this statement and notice something a little bit interesting about it now. What we're saying at this point is that regardless of the cutoff point that you choose, there's going to be a further thing past that cutoff point so that whenever you take an open interval, some open interval is going to have it be the case that f sub n of x is less than 0. That is that f sub n of x is less than 0 means that this point cannot be inside of this set. Now that's true for any open interval. So we actually, if we look at how this first sentence is worded, the way that it's worded is telling us that no set S sub n can contain an open interval. Let's say, for example, like we're looking at S sub capital N, for example, using this capital N as a result. For all S sub n, any set that we might work on, then any open interval that you might choose inside of 0, 1 still is going to have some further sequence, some further function in the sequence past that point, and something inside of that open interval so that this thing is not inside of the set. So working through this a little bit and looking at our definition of S sub n down underneath, which would say that actually for all things past a cutoff point, you have that the function is greater than or equal to 0. We see these as negations of each other. That is, by our first sentence, we are saying that S sub n or S sub n bar has no open intervals. There's no open intervals I. What does that mean? If you have a set with no open sets inside of it, that means that the interior, which would be an open set otherwise, can't have anything in it. Otherwise, it would be an open set. It would have an open interval, which means that S sub n closure interior is the empty set, so S sub n is nowhere dense. We now can finish the proof. We've said that 0, 1 is a countable union. Got to write it over here in this tiny little spot, a countable union of nowhere dense sets. Got to keep writing smaller so as to be able to make room of it, of nowhere dense sets, which is a contradiction with the Baire category theorem. And when I write this out in the completed notes, it'll look a lot nicer. But so we just shown that the set of 0, 1 is the countable union of all of these S sub n when we've shown their closure interior is equal to empty set so that they are nowhere dense. We've shown that 0, 1 is a countable union of nowhere dense sets, which is a contradiction with the Baire category theorem, which means the only thing that we can do is say that the thing that we assumed, the opposite of this problem, is itself false, which means that the original problem statement is true. A crazy theorem throughout from beginning to end, but this is how the problems in this world typically go. Let me go ahead and kind of work a little bit just to kind of make this a bit neater as far as the way that I've written this before I very quickly go through an optional problem that shows a little bit more about how the Baire category theorem can be used. And that does it for our last video lecture of content. I went ahead and with this last problem put down a solution that I'll put into the completed notes in case you'd like to look into it, but it's not going to be at the level of what we see on our homework or anything like this. This was just something that I thought was cool, was that you can actually show that certain spaces can't be made complete by changing the norm on these spaces. So I went ahead and put this in the completed notes. I hope that you can work through this example that we've been showing as well. And if I get some time, I want to try and make another kind of attempt at showing another example of how we can utilize the Baire category theorem effectively, much like how we did in this problem and in many other cases. Now, there's a lot going on in many of the different pieces of this problem, and it's going to take some time to kind of parse through them all. This is definitely the type of problem you want to be seeing multiple times because the more times you're exposed to it, the better you're going to feel about it as you go through it. So try working through this step by step. You'll realize that these problems have a specific formula to them. In fact, I actually have a database full of problems that are much like this. I'll go through and see if I can share some of those problems so that you can be reading through those proofs so that you can see how those work. The goal here is to try and get you more and more used to coming up with some of these arguments yourself. If you're continuing to go from this point on to higher levels of mathematics, this is our leaving point, our touching point, our last touch and go point for this point of analysis. And many of you are going to want to go farther than this point. And you will see that as you go farther from this point, more and more problems are just going to ask you, how are you going to solve it? There's no structure going to be given to you. It's just, how do you do it? How do you take the things that are given to you in the theorem and in the problem and the structure and start working with them? Let this be a tool to strengthen you to go off and use more and more tools, get them into your belt, ready to take on the world with some of these math problems that you see in the future. But that covers the Baire category theorem, our very last topic for this class. It has been a joy, y'all. Thank you so much. Have a wonderful day.